All right, so now what I'd like to take a look at are some basic identities. And what we're going to start doing is thinking about how can we verify some really complicated identities with trigonometric functions actually hold true. And the way we're going to see that is by starting off by just finding some really basic facts about how the trig functions sort of interact with themselves. So it's sort of like a little trig fest, you know, trigs playing together. So let's start off just very simply by first of all just recapping what trig is all about. So here's a real fast recap of trig. We'll start off with this little right triangle. I'll call this angle theta. So this will be the adjacent side. This is the opposite side. This is the hypotenuse side. And so what do I know? Well, I know that, let's see. In fact, let me make a list over here of things I know. So I know that sine of theta equals opposite over hypotenuse. I know that cosine of theta equals adjacent over hypotenuse. And I know that tangent of theta equals opposite over adjacent. So one thing that we can see is, well, what would happen if I just took sine and put it over cosine? So if I took sine over cosine, what would this equal? Well, let's see. Well, sine is opposite over hypotenuse, so that's sort of opposite. Not sort of, it is opposite over hypotenuse. And then what's cosine? Well, cosine is adjacent over hypotenuse. And when I invert and multiply, I see that, in fact, the hypoteni cancel because I have a hypotenuse on the bottom, and when I invert this, watch what happens. Whoop, I have the hypotenuse on top. And so what I see here is opposite over adjacent. And what's the name of that ratio? Well, that's exactly tangent. So we just proved, in fact, our first basic identity, that tangent equals sine over cosine. Tangent equals sine over cosine. So that's a really important one to remember. And not hard to verify for yourself. Just a matter of thinking about the definitions, and you're sort of on your way. Now, how else can we use that triangle? Well, we can use this triangle because since it's a right triangle, I can actually report sort of the Pythagorean theorem. So what's the Pythagorean theorem say? Well, the Pythagorean theorem says that one leg squared plus the other leg squared is a third leg squared. So we have adjacent squared plus opposite squared equals the hypotenuse squared. Okay, now what could I do here with this? Well, let me divide everything through by the hypotenuse squared. So I'm going to divide everything through by this term, just to see what I get. If I do that, I would see adjacent over hypotenuse, all squared, plus opposite over hypotenuse, all squared, equals 1. I just divided everything through by the hypotenuse squared. But look, what do you see? Well, adjacent over hypotenuse is just cosine. So this is just cosine squared. And opposite over hypotenuse, well, that's just sine squared. So on this side, I see cosine squared plus sine squared equals 1. So in fact, that is another identity, which just follows from the Pythagorean theorem. So that one says that, I'll write this way, sine squared theta plus cosine squared theta will always equal 1. And that's just the exact same statement as the Pythagorean theorem, but in a trig kind of form. And really easy to prove. It's literally just this proof right here. Just take the Pythagorean theorem, divide through by hypotenuse, and you get this. What if we divide through by something else? Suppose, for example, we divide through by, well, what can we divide through by? Let's divide through by adjacent. If I divide through by the adjacent here, what would I see? Well, if I divide through by adjacent, everything through by adjacent squared. So this becomes a 1. This becomes an opposite over adjacent all squared. And this becomes a hypotenuse over adjacent all squared. So what do I see now? I see 1 plus, and what's opposite over adjacent? Well, opposite over adjacent is just a fancy way of saying tangent. So in fact, this is tangent squared. So this is tangent squared. And what's hypotenuse over adjacent? So what's that? Well, hypotenuse over adjacent is sort of the flip of adjacent over hypotenuse, which is cosine. So what's the flip of cosine? Well, that's secant. So this would be secant squared. So I just discovered another identity by using the Pythagorean theorem, I see that 1 plus tangent squared equals secant squared. Equals secant squared. So there's another identity. So that's pretty cool. And I just got that by taking this identity, basically, and dividing everything through by cosine squared. Right? Because here I'd see sine squared over cosine squared, that's tangent. Here I'd see a 1, and here I'd see 1 over cosine squared, which is secant squared. What if I took this thing and divided everything through by sine squared? If I divide everything through by sine squared, here I would see a 1. So I'm taking this equation and dividing everything through by the sine squared. So here I'd see a 1. And here I'd see a cosine theta over sine theta all squared. What's cosine over sine? Well, if sine over cosine is tangent, cosine over sine must be cotangent, the flip. So in fact, this must be cotangent squared theta equals 1 over sine squared. Well, 1 over sine squared is the same thing as cosecant squared. And so I see now a third identity. All these last three identities just followed from the Pythagorean theorem and dividing everything through by one of the terms. So in fact, these are three really fundamental identities, which are really important to sort of remember. Now I'll tell you the truth. The truth is I only remember basically these two. This one sort of makes sense to me. Tangent is sine over cosine, and sine squared plus cosine squared is always 1 if it's of the same angle. And these other ones just follow from this one if I divide everything through by either sine or cosine and so forth. So in fact, these you don't have to memorize. In fact, to be honest with you, I don't memorize these. I just know this one and can always find these by dividing everything through by the cosine, which gives me this one, or dividing everything through this by sine, which gives me that one. Anyway, okay, fine. Now, how can you use these things? Well, suppose you actually you knew just one trig value of an angle, and you want to find all the rest. Well, it turns out you can actually use these inequalities to actually find those other values. So up next, what I'm going to do is take a look at how just using one information about one trig function at an angle, we can actually resolve all the trig values just by using these identities. We'll take a look at that coming up next. I'll see you there.